Hi guys, Kenna here. Today we're going to be looking at interference and diffraction. So we're getting towards the end of our unit on the properties of waves, especially looking at electromagnetic spectrum. And we're going to kind of look at interference and diffraction today. And next class we'll go ahead and look at lasers and holograms. So let's go ahead and jump right in. Essential questions for today. Number one, what is diffraction? Okay, let's take a look at what that is and how that relates to the properties of waves. Number two, how are shadows created and why are they not always created the same way? Or are they? Number three, what is interference and how do constructive and destructive interference work? Number four, what is the double slit experiment and what does it teach us? We talked about this a little bit already earlier on when we were looking at light in our waves unit. And then lastly, what is a spectrometer? Okay. So the wave-like properties of light cannot be seen directly. In the notes today, we're going to explore the experimental evidence that demonstrates how we know that light behaves as a wave. Like sound and water waves, light shows an interference pattern and diffraction. Light also has the property of polarization, and many inventions use these properties of light. Lasers use interference of light waves, and we separate out colors with a diffraction grating. Sunglasses and LCD screens use polarization. So what exactly is diffraction? Well, if you can imagine shining a flashlight on a wall through a slot in a piece of cardboard. On the wall, you see bright light where the light rays pass through the slot. You see shadow where the cardboard blocks the light rays. But if the bulb was very small, there's a sharp edge to the shadow, showing you that light rays travel in straight lines. But if the slot is very narrow, the light on the screen looks a little different. The light starts to spread out after passing through the opening. This spreading effect of light going beyond just what you would expect from the slit is because of what we call diffraction. So diffraction is a wave behavior. This is not something that particles do. And diffraction occurs when a wave passes through an opening not too much wider than the wavelengths of the wave. A small opening acts like the center of a new circular wave. And so seeing diffraction with light is evidence that light behaves as a wave. So what does this have to do with shadows? Well, if you look at an ordinary shadow, it often has kind of fuzzy edges. But this is because of a different reason. When light comes from a light bulb, light rays from many different points on the bulb are casting different shadows in different places. The width of the fuzzy edge depends on how far away the light bulb is, how big it is, and how far away the screen is that you're projecting upon. You can see diffraction is a shadow cast by a sharp edge with light from a laser. The edge of the shadow has ripples in it. The ripples are caused by the diffraction. You don't see that with white light because white light is actually a mixture of different wavelengths. We've got the red on the long end and the violet on the short end. So a laser is going to be collated into very specific amplified wavelengths. And this makes a pure color with a single wavelength. So interference is a property of waves, and we've looked a little bit at interference already when we first introduced you to light and when we first started talking about the double slit experiment and how that goes ahead and teaches us that light is a wave. Now, in 1807, Thomas Young proved that light was a wave when he came up with this experiment because he showed that two beams of light would actually interfere with each other. In this famous experiment, he let a light pass through two very thin slits, and after passing through the slits, the light fell onto a screen. If light were not a wave, then the pattern should just look like the diagram I'll show you here in a second on the left. Okay, there you go. So if light were not a wave, you would just see two lines as the particles went through those two slits and you'd be done. However, when you go ahead and take a look at this, the light at any point on the screen from those does not show that, but instead shows a pattern of light and dark bands, with the brightest obviously being in the center, where there's actually a block between the two. Okay. And so if we take a look at this, this is what you actually observe. This is an example of light behaving as a wave because it creates this interference pattern due to the diffraction of the waves as they go through the two slits. Then they develop this interference pattern where you get both constructive, where they add to each other, and destructive, where they cancel each other out in terms of their interference. The double slit experiment is very strong evidence that light is a wave because an interference pattern can only be created by the addition of waves. So right now, I want you to think about each slit as the source of its own circular wave. Think about like throwing pebbles into the pond. Okay. The waves from both slits are exactly in phase when they leave the slit because the light from both slits came from the same wavefront. Straight ahead, think about this in line with the slits. The wave reaches the screen in phase and there's going to be a bright area on the screen. Next to this bright area, the light from each slit hits the screen out of phase because one of the two waves has to go farther than the other, and so then you have a trough that lines up with a crest. Well, when this happens, because they're the same wavelength, they actually cancel each other out, and you end up with a dark line or a dark band. So the bright bands in an interference pattern are where the light waves from both slits are in phase, okay, a crest and a crest, okay, or a trough and a trough. And this is known as constructive interference. The dark bands are going to appear where the light waves reach the screen out of phase, a crest hits a trough, and this is what's known as destructive interference. So if we take a look at these ripples, okay, in the pond with the water strider, or the ones with light down below, you can see that light, dark, light, dark pattern. Again, constructive interference, when you add two waves that are in phase, they end up amplifying, creating a brighter spot in the bright spots and a darker spot in the points where they get destructive interference, where a crest meets a trough and they cancel each other out. Now, it's a pretty cool concept, and while I think we can understand the basics of it, there's always kind of a deeper level that we need to kind of keep in mind. So I'm going to go ahead and let Brian Green go ahead and explain the double slit experiment to you in a little bit more detail.
We can get a pretty good feel for the double slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you'd find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit.
The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller.
You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing: waves. Waves do all kinds of interesting things, things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they'd cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So, how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave?
Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave.
A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave. And now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described.
Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave.
That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron,
I can never predict where it will land. But if I use Schrödinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on.
these kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise, so long as you can accept that it's all about probability.
Okay, so this has to do with that wave-particle duality, this idea that what we think of as a particle is actually, when in motion, behaving like a probability of wave. There's a chance of finding it at any one particular place, which makes sense when you start thinking about these interference patterns, when you start thinking about diffraction. And so we have something called diffraction grading. Now, diffraction grading creates an interference pattern very similar to the pattern for the double slit experiment. A grating is actually a series of thin parallel grooves on a piece of glass or plastic. When light goes through a diffraction grating, each groove scatters the light so that the grating acts like many parallel slits. If you go ahead and look at the two slits in this particular example on the right, the second row down, this is very much what we would expect from a double slit experiment. Okay. Now, when you go ahead and start adding more and more, you get to see that there are more sections that get blocked out because the probability wave then ends up creating more and more different waves, which are going to have a greater amount or a greater chance of canceling each other out. Okay. So when you shine a laser beam through a diffraction grating, and I wish we were in person to be able to do this, most of the light goes straight through it. And this is going to produce the brightest spot known as the central spot. And this is directly in front of the grating where the light passed straight through. However, some of that light is also going to be scattered off the many grooves in the diffraction grating and create interference patterns. The interference of light scattered from the grooves is what causes the additional bright bands on either side of that central spot. Okay. Now, if you were to look at this in terms of a light wave, you're going to have a brighter, wider band in the center, and then you'll have additional bands as you continue outward, but they're going to be less bright as time goes on. So we have the central spot, which is the main one, and that's going to be the brightest. The next is going to be called what's the first order. Okay, these are the second brightest after the central spot, second order, third order, so on and so forth until you can't see these peaks anymore. So as you continue on through here, you're going to see these diffraction patterns produce interference as the incident light ray or laser beam comes through the diffraction gradient, and each one you move out from that central spot is going to be less bright. Okay, first order, second order, third order, fourth order, so on and so forth. Now, like the double slit experiment, a bright spot forms when the light waves have two adjacent grooves arrive in phase, and when two waves are out of phase, you go ahead and get a dark spot. Now you'll see that it doesn't stay just bright or just dark, but you'll have those interference patterns where they're a little out of phase, but not so much that it completely cancels out. And so you actually see going from a really bright spot, and then it'll kind of get dimmer, 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 dimmer until it goes to a dark where they actually cancel each other out. And then it will slowly fade back in from dark just a little bit brighter, 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 brighter until it gets to the full brightness of the uh, first order peak that we would go ahead and see. So because of the location of the bright spots depends on the wavelength, different wavelengths of light, however, are going to make different spots with respect to how it breaks off from that central spot. Because remember, red wavelengths are longer, going through Roy G. Biv until we get to violet, where the wavelengths are shorter. And this leaves us with spectrometers. When light with a mixture of wavelengths passes through a diffraction gradient, so think about white light, each wavelength makes a bright spot at a different place on the screen. And as a result, the grating spreads the light out into its separate wavelengths, which is why you see a rainbow when looking at bright white light through a diffraction grating. Now, a spectrometer is a device that uses a diffraction grating to create the spectrum. The spectrometer has a printed scale that allows you to read different wavelengths of light directly from the pattern of light going into the grating. And so you'd see something like what you see right here. You got your Roy G. Biv, okay, and then there just happens to be a little purple there on the end. All right, well, that's what I've got for you guys today. Take care of yourselves, stay happy, stay healthy, stay safe, and I'll talk to you soon. All right, take care of yourselves. Bye-bye.